In this video, we are going to continue to speak about the Posicast control. This is the video 3 of the journey, and we are going to introduce a Gantry-Crane control problem. So, we are going to consider a simple mathematical model of this system, which is composed by a trolley or a car, this one here, which is going to be actuated by a force. And then we have the suspended load with a mass m. The length of the cable is L, and then we got here the angle of the rotation of the cable and the displacement x. So I'm not going to go to details. We are going to consider two transverse functions. The first one relates the angle theta with the displacement x, and it can be represented by a second order model, as you can see here. And then we got another transfer function who relates the displacement x with the force, the applied force to the car F. This is can be represented by a fourth order model, which is this one. I'm not going to go to details about the models, but you can find information in this paper that we published in 2013, Gantry-Crane Control, a Simulation Case Study. So, in this case, this was used in experiment for mechanical engineering students for control, the first course of control systems. We can use these settings. The trolley mass is 0.25, sorry. The suspended load is 0.5 kilograms, and then we got this length of the cable, and this is the gravitational constant. So using these values in this first model, G1, we can do some introduction simulations. So we are going to evaluate this damping factor for the model D, and so this D depends on B2, and B2 is the suspended load damping factor. So with several values to the damping factor, we can have several didactic simulations. So we are going to use this model, and the first case, case 1, is no load damping. So we are going to assume that this is a theoretical situation, ideal situation, where in this case no damping at all in the load. So P2 is 0, D is 0, and the model becomes reduced to this simple equation here, as you can see here in the bottom. So we are going to assume that we are going to apply a step in the position of the X, and you are going to see what happens to the deflection angle of the cable. Okay, we are going to assume ideally that the car can move with a step. Okay, so we can evaluate the position of the mass, the suspended mass, with these two equations for x and y, depending of the angle theta. So the first case, with no load damping, we are going to assume that we are going to apply a step with amplitude of 0.7 meters, and so what happens is no damping, so we got a perfect oscillation, oscillatory oscillation. We can see here that this is 0.7, and this is the angle, and this is the x. So we are going to see, it is interesting to see the simulation. So I have done a few years ago a kind of simple, we have done a simple graphical interface in MATLAB with just some very elementary drawings. And in this case, you can see that we have here the initial position. This is the final position, and so there is a jump here, of course, ideally. And then we got we can see here the oscillation from the beginning to the end, and we can also see this in a kind of movie. Here you see, so you cannot see here that there was a jump from this point to this point, but of course there is no damping, so it's like a pendulum that is always be rotating without stopping. Okay, so moving on, we can okay, so if now we consider some damping with this value 0.3 in the load, now the model becomes this one in Laplace domain, and of course now we got the under damped response, which is this one that you can see here in the bottom. And we are going to do, so you can see here the drawing, there is a drastic change from step from this point to this point. This point corresponds to 0.7, and of course in this case it's going to be reducing the oscillation because of the damping. We can see also the video here, and as you can see now there is damping, but it's going to take a while, so until the load stops oscillating. As you can see, I'm going to speed up this a little bit more until, okay, it reaches the steady state position. Okay, now, so, and finally, with increasing the damping to this value 0.75, the oscillation is even more damped, and again, a simulation for this movement is this one. So in this case, this is going to be much faster, as you can see here. It stops the movement in some simulations. So this is a kind of introductory simulations for second order systems with this simple animation done in MATLAB. So it concluded. So I'm going to speed up this. And okay, these are the three overlapped responses for three cases of damping in this transfer function. And we are going to continue this simulation experiment in the next video, but this one concludes video 3. So thank you very much for watching.